Moons is the most complex instrument we have built for astronomy.
The thing that I'm most proud of is the diversity of engineering we've done here. That front end has tiny robotic arms that position to within a few microns, that weigh tens of grams, that are in these incredibly high precision parts. And then at the other end, you've got the 8 tons of cryostat with the 100-kilogram blocks of glass that we've maneuvered, that we've positioned. And it's the same team, this kind of international consortium on different parts, but that team is pulled together to do this kind of huge range of different things. Not to mention just the mechanics, there's the precision of the optics. Some of the biggest lenses ever manufactured in Italy are part of this project. We then have all the electronics, all the control systems, and then there's a whole level of software beyond that as well. It's such a hugely diverse range of things that we've all had to pull together to make work. And the fact that we as a fairly small team have managed that, and that we have done it so well, is a huge point of pride for me.
It's extremely difficult to have 1,000 fibers, small robotic arms that need to move very, very precisely into their positions of sky. I'm talking about microns, right? So hair size of errors in the robots that are locating the fibers into the targets has a significant impact. It has two. If it's extremely bad, you might be completely off on getting a different object than what you think you're observing. That is absolutely not acceptable. In the other case, what you can have is that small errors of it. So you have your star, you have your fiber with a small separation. That means you're losing throughput. You're losing the amount of light that you're capturing into the fibers, ultimately into the spectrograph. So you will not have sufficient signal in your final spectrum to do the science you want to do. So we need to be extremely precise, and an immense amount of work has gone in the design, in the testing, in the calibration of each one of these robots individually to make sure that they are able to go physically exactly where we want them, so that they can go on sky when we are at the telescope exactly where we want them to go. On the other hand, the spectrograph itself brings an enormous amount of difficulties and challenges from an engineering perspective. The multi-object capability comes with a very big challenge, which is the size. The more objects you're trying to observe, the bigger your spectrograph has to be, because you need to collect and pack more information of light into your final detector. The more fibers you're fitting in, the bigger your spectrograph is meant to be. In the case of moons, 1,000, that makes it already quite big. The spectrograph, 4 meters tall, 3 meters wide, that is extremely challenging already. But you need to add into it that we are observing in the infrared, which forces us to have a cryogenic vessel around it. So we're operating all of these immense optics and cryogenic mechanisms in temperatures in which are extremely challenging from a point of view of the design, of the maintainability, and we need to make sure that they're operating very reliably in these conditions. Every single part of moons has been a challenge from a point of view of engineering, where we have been in the need of working with industry, very close with industry, in order to ask them so that they can adapt their techniques and adapt what they do, so that they could provide us with the optics or either the mechanisms that we have put in moons. Every single aspect of it has been a challenge.
What we're trying to do here is take 1,000 individual images of stars and put them onto sensors which are kind of about that sort of size. To squeeze all that information on and get the resolution that you need, you kind of have certain bounds about how big you make your image. That means that defines how big your optics are, and our optics in moons are about 0.5 meter or bigger across. When you take that size of camera, you make 6 of them, and then you have to feed all the light in, you end up with something pretty much the size of moons. If you want to do this much science with this kind of system, it's going to end up being this big. It's just the nature of the physics. Because moons works in the infrared, I said we're looking at heat, this creates a whole bunch of engineering challenges, particularly around cryogenics. So the best way of imagining this is if you're in the house at night time, you're trying to look out the window and the lights are on inside the house, you only see your own reflection, you can't see out. To see out, you've got to make things dark inside, you turn the lights off. We have to do the same thing in the infrared, but here we're talking about heat. So our version of turning the lights off is making it cold. And when I talk about cold, I mean extremely cold. This has to be colder than the things you're looking at. So we're talking about over minus 100 degrees Celsius. This is absolutely frozen inside. So everything that we build has to work at those kind of temperatures. Everything inside this spectrograph behind me has to work at those low temperatures. This has a whole bunch of challenges. Not only do we have to make the entire structure and everything inside that temperature in the first place, and now keep in mind Moons is very big, so it's about 8 tons of material that we have to bring down to those incredibly low temperatures. Then once you have everything at low temperature, anything we've got inside there, all the metals start to shrink, all the glass starts to shrink. We have to make sure all that shrinkage is correct, otherwise you risk damaging things. We have to make all our mechanisms, all our motors, all our linear slides work at those low temperatures. And generally speaking, anything you think of that is like an oil or a lubricant at room temperature tends to form a glue when it goes cold. So everything has to be very, very custom, very specific. And then an additional level on top of all of that is we have to position all our optics very precisely together. We're talking fractions of a millimeter in the right place. As I mentioned, everything shrinks when it goes cold. So what we have to do warm is put everything very accurately in the wrong place, so that when we go cold, everything ends up accurately in the right place. And that's just kind of one of the aspects of the engineering that we have to deal with. To maintain the system at temperature, we use something called pulse tube coolers. These are just behind me, and these essentially use liquid helium being pumped through them to basically work like a supercharged freezer to keep it down at that very low temperatures. The difficulty here is to bring our 8 tons of instrument down to the temperatures we're talking about on just those would take months. So we have to find a way of kickstarting this process. And the way we do that here is that we flush an awful lot of liquid nitrogen through it. We flush about 5 tons of liquid nitrogen through this system in 48 hours. And that sheer kind of weight of liquid nitrogen going through the system pulls it down to temperature, and then we can maintain it essentially indefinitely on the small coolers that keep it running. But once we finish getting everything built here within Europe, we have partners from ESO coming across to essentially inspect our work, to verify that we are ready to ship to them. They will not accept this until they are happy that it is going to work and do everything that they expect it to. Once we have that signed off, we box this up, we ship it by boat across Chile, and then drive it up the mountain. Once we get to the mountain, there's sort of 2 phases to the on-site assembly. The first one is in an integration hall, which is not on the telescope, but is still at the observatory. Here we will unpack everything, we will build it all up, and we kind of do verification tests to ensure that it works as well there as it did when we were in Europe, make sure nothing went wrong in shipping. We then have another stage gate with ESO who confirm that everything is as they're expecting and that we are now ready to go onto the telescope, which is the really expensive part and the very time critical part of the process. Once everything's working in integration hall, we drive the last little bit up the mountain into the telescope. We then bring all our parts into the telescope. One of the complexities of Moons, because of the size, is that we don't fit through the main door of the telescope anymore. So we actually have to hire a large crane and get lifted in through the slit in the top of the dome, which is a horrifying moment. We have to lift this thing up and drop it very carefully onto the platform internally. Once that's done, we screw it all down. We then spend some more time fitting it, getting it up and running on the platform, plugging it in, running all the cables, getting the network, computers. At that stage, we do some basic on-sky testing to confirm that it's working, and we hand over from the on-site assembly phase to the commissioning phase, which is where our local scientists take over to get it all working on Sky. And once that's done, we hand it over to ESO to begin operations.